In this lesson, we're going to take a look at area and the law of sines. And what this will entail is using trigonometry to find the area of triangles when we might not otherwise be able to. Now, hopefully everybody is well familiar with the standard formula for area of a triangle. A equals 1/2 base times height. And of course, that base and height have to be perpendicular to one another. So using the triangle that is shown here, if I were to drop an altitude from angle B, that would be my height. But if all the information that I have is about the physical structure of the angle of the triangle itself and not that height, how can I go about finding this formula or finding these values? Arbitrarily, if I were to pick angle A and know its angle, and then also have these pieces, what I can find is that from the perspective of angle A, dropping this altitude creates a right triangle. And using our basic trig ratios, the sine of this angle A is this height, my opposite side, divided by the hypotenuse, which would be side C. So writing this out, I would end up with the sine of angle A equals that opposite, which is the height of my triangle, divided by the hypotenuse for it, which would be side C. Solving for h, I end up with C times the sine of A is that height. Now, using substitution in for that piece, what I could end up with is changing my formula to area is 1/2 times side length B times this height, which is C, times the sine of angle A. So in geometry, you should have been introduced to something called Heron's formula, which is a way of knowing or calculating the area of a triangle if you know all three side lengths. And of course, we have our 1/2 base times height. But now, if I know two sides and their included angle, or as we would state it in geometry, a side angle side information set, I can go through and compute the area of my triangle. And we can repeat this using any two sides and their included angle. Same derivation would happen, just changing around the pieces. So I can end up with area is 1/2 BC sine of A. I could also do 1/2 A times C times the sine of angle B, or I could do 1/2 A times B times the sine of C. So as long as I know any two sides and their included angle, I have a way of computing out the area of my triangle. So let's do a little bit of practice with it. Okay, so we're going to compute the area of each of these triangles from the given information. Okay, we're going to start out with area here is 1/2. Now I don't have anything labeled as A, B, and C, but all I need is two sides and their included angle. So in this case, I can go 7.3 meters times 5.6 meters times the sine of 40 degrees. Okay, running that through my calculator, I have an area of 13.14 square meters. Okay. Now again, in this case, we are using our 7.3 as our base, and we're computing the perpendicular height as coming out of this 5.6 sine of 40 using those trig ratios. Okay, so what does it look like on our next triangle? So again, we're going area, and we're going to take our two sides, 1/2 of 18.6 times 21.1 times the sine of 28 degrees. Okay? And again, rendering that through our calculator will give us an area of approximately 92.12 feet squared. And of course, including units and making sure, because it's area, those units are squared, we want to label all the pieces possible. If no units are given, simply say units squared. Okay, so computing area using trig can be helpful. Again, knowing any two sides and their included angle allows us to carry this out. We don't necessarily have to have right triangles anymore, or even that height piece. So what else can we do with this? The great sine ratio, taking all these being the same, are 1/2 BC sine A, or 1/2 AC sine B, or 1/2 AB sine of C. If I were to take all of these and simply divide them by 0.5 ABC and conduct that out to all of them, in the equation, of course, division property of equality, I divide all parts by the same thing, then it maintains its equivalence. What I will come out with is the sine of A over side length A is equal to the sine of B over side length B, which will be equal to the sine of angle C over side length C. So in any triangle, the sine of an angle and the length of the leg opposite, or the side opposite it, will be constant through that triangle. Of course, applying our properties of congruence when it comes to ratios, we can also take the reciprocal of all these and say A, side length A over the sine of angle A would be equal to side length B over the sine of angle B, should be equal to side length C over the sine of angle C. And as long as I have any two of these fractions, I can solve for what's missing. If what I'm looking for is a missing angle, these top ratios become more helpful. If I'm looking for a side length, placing the side length on top becomes a more useful piece. And from these, I would be able to go through and find missing parts. Now, there are some cautions that come up when using this. This is called the law of sines. That occasionally, because on my basic triangle, or on my basic information from my unit circle, we get some corresponding values that in quadrants 1 and 2, if, say, the sine of 30 degrees is 1/2, well, the sine of 150 degrees is also 1/2. So how do I know which of those two angles was intended if I'm trying to solve for a missing angle? We will discuss that here in a few minutes. It is something called the ambiguous case, because with ambiguity, we're not certain as to the outcome. It takes a little bit of extra thought, but not a whole lot of extra work, simply understanding this concept that an angle, theta, and its supplement, 180 degrees minus theta, will render out the same sine value between the two sides. So just being aware of that. Of course, in a triangle, I can't have any one angle be over 180 degrees, so I don't have to worry about the negative side of this circle from that y perspective. So let's use the law of sines in solving out a triangle. So we're going to solve the triangle from given information. And what we mean by this is anytime you're asked to solve a triangle, it simply means to find all parts, all side lengths, and all angle measurements. Okay, so for what I have given here, I know that angle R is 110 degrees. I know side length T is 7 units, and side length R is 9 units. Going off of the convention that an side length is lowercase letter of the angle opposite it. So here we have angle R, that means this is side length R. Angle T, side length T, angle S, side length S. So what other pieces of information do I need? Well, I need to know these other angles and this one side length. So I start out in law of sines with a known opposite pair. In this case, that is R and angle R and side length R. Then one other piece. Well, I know side length T, however, I do not know angle T. When I'm starting out with an angle that I know to be over 90 degrees, an obtuse angle, the law of sines becomes very helpful because the only options left are acute angles. And if I were to start out with an acute angle and not necessarily a picture to depict it, then I'm going to be running danger of that ambiguous case. So let's start out with the ratios and see what we can solve out from there. So let's go that the sine of angle T over side length T, which is 7, is equal to the sine of angle R, 110 degrees, over side length R, which is 9. Now solving this for T, I'm going to multiply my 7 out of this denominator. So I have the sine of T equals 7 times the sine of 110 degrees over 9. Now in order to get T by itself, of course, I'm going to take the arc sine, so T equals the arc sine of this fraction, 7 sine 110 over 9. And then running that through my calculator, I come out with T is approximately equal to 46.959 or 47.0 degrees. Okay, so I get 47.0. And of course, knowing that the angles inside of a triangle add up to 180, angle S will be 180 minus my 110 minus my 47. And so I come out with angle S having a value of a simple 23 degrees. Okay, so we'll label that in here. 23.0 because the 47.0 is an estimate as well. Now I need to find the side length for S. So I'm going to grab my information and set up a ratio involving that. So S over the sine of S, which is 23 degrees, will have to equal, and I can take any other opposite pair, since the angle for T was an approximation, I'm going to stick with my R pair that I know to be true, 9 over the sine of 110. Okay, solving for S, I'm going to multiply that sine 23 out of the denominator, so I have 9 times the sine of 23, all divided by the sine of 110. Okay, sines do not cancel. It is not that type of mathematics where we can factor out an operation like we would numbers. But running this through, I'm going to get a side length of approximately 3.74 units, or rounding to the nearest tenth like I have everything else, a simple 3.7 units in length. So from a little bit of information, we were able to find all side lengths and all angles. We now have what is constituted as a solved triangle. Okay, and we can carry this out simply using the appropriate ratios. Notice that when I was looking for an angle, the measurement of angle T, I put the sine portions in the numerator and my side lengths in the denominator. When I was looking for a side length, side length S, and I had the other information, I put those side lengths in the numerator and my sine of the angles in my denominator. Okay, so we are able to solve out any triangle as long as I start out with one opposite pair and then any other piece. If I were to start out with an opposite pair and a single angle, I could then, using 180 degrees as the sum of the angles, find the third angle, and then start matching up for opposite sides. If I have two sides and one opposing angle, then I can use that as well to find the missing angle and then compute out as we did here. What I cannot use the law of sines for is if I had two sides and the included angle, the information that we need in order to find the area of a triangle, which we just discussed, that will take something else called law of cosines, which is typically learned after the law of sines. Okay, let's take a look now at that ambiguous case and see what is happening with it, okay, and how to detect it. So multiple triangles are occasionally possible based off of our initial setup. Okay, so triangle ABC, we know the measurement of angle A is 29 degrees, side length A is 17, side length C is 18. So the first thing I'd be able to do, because I do have one opposite pair, is set up that ratio. Then I have this other side length, so I can solve for a missing angle. Okay, so I'm going to say that the sine of angle C over 18 equals the sine of angle A, which is 29 degrees, over that side length of 17. And multiplying my 18 out of this denominator, and then taking the arc sine all in one shot, what I'm going to end up with is C is equal to the arc sine of 18 times the sine of 29 over 17. And when I run that through, I get C to be approximately 30.9 degrees. Okay, so now how do we find if this could possibly give us two triangles? And the question comes down to how big would the third angle be if we have this situation. So if I look at my unit circle, I came out with a value of 30.9 for this angle. Question is, what does it supplement? Well, the supplement will show up right here, and that is going to be 149.1 degrees. Okay, that will always be true. The sine of 149.1 is the same as the sine of 30.9. So how do I know that my calculator meant this one and didn't mean this one? That comes back to a discussion of our domain and range. The real question is I know that angle A has to be 29 degrees. If I were to take this version of my arc sine, and include this angle, does it still leave me room for a third angle? Okay, going off of the information that I already have, I can easily make the statement that 180 degrees minus my 29 minus my 30.9, looking for angle B, I get angle B coming out with a value of 120.1 degrees. Well, if I were to use the other one, B being 180 minus 29, which I know to be true, minus the 149.1, which I speculate might be true, does it leave me room for another angle? And if I do that subtraction, I come out with an angle measurement of 1.9 degrees. Okay, so I can have either of these situations. I can use highlighting them into the same sets here. I can say angle A is 29, angle C is 30.9, and angle B is 120.1. Or it might be possible that I'm looking at angle A being 29, angle C being 149.1, and angle B being 1.9. Okay? Both triangles are possible. When the ambiguous case does not yield us multiple triangles, is that if I were to carry out this subtraction and end up with angle B having to be a negative value, or in other words, the angle that I know plus the supplement to the angle I computed, if those are over 180 degrees or equal to 180 degrees by themselves, they don't leave room for a third angle. Okay, so as long as a third angle is possible, then we have the possibility of two triangles, and it's our ambiguous case. So what I would need to do now is to run my law of sines for both of these situations. Angle B being 120.1, how long would side length B come out? If angle B is 1.9 degrees, how long would side length B come out? So in either case, our setup would look like this for our two different situations, that B over the sine of the 120.1 would equal 17 over the sine of 29. Now running that computation, we come out with B being approximately equal to 30.3 units. Or I could be looking at B over the sine of 1.9 degrees equaling 17 over sine of 29. Notice in both of these, I use my known pair to begin with. In this case, I come out with B being approximately 1.2 units in length. And that makes sense because a larger angle will open to a larger side. So if I have a very small angle measurement, I'll have a very short side length. If I have a large angle measurement, I will have a relatively large side length. So law of sines, any side length and the sine of the angle opposite will be consistent in the triangle. And occasionally we do run into multiple triangles possible. Always test for the ambiguous case, but be aware that it doesn't always happen.